All right, we're back. We are on page 10 of Notes 15 of Calc AB. We just, it took 2 videos to go through a proof, and it's not even like the most rigorous proof in the world, but it took 2 videos, mostly because I can't draw stupid rectangles, and I think we all know that, and it's been a problem in the videos for several sets of notes now. But anyway, Fundamental Theorem of Calculus, one of the greatest things humanity has ever come up with. It's amazing. Newton, Leibniz, probably a billion other people involved. Really, really interesting. So it says if f prime is continuous on the closed interval, it's actually really important that it be continuous. You're going to kind of forget that because you don't run into discontinuities all that often. It's got to be continuous. If f prime is continuous on the interval from a to b, and f of x is an antiderivative of f prime, then the integral from a to b of f prime of x dx is f of b minus f of a. It's amazing. Like, it's insane that we can do that. We're going to do it. The next set of notes is about using it. It's a weird choice that I made when I was writing the notes, that like we come up with it and then we like basically never do it. We're going to do it. But fundamental theorem, integral from a to b of f prime of x dx is f of b minus f of a. So it's where you end up minus where you started. It's displacement, basically, which we've actually already knew. But we proved it. Mean value theorem is involved there. You have to make a lot of really judicious choices that as a human you would probably never make by hand, but whatever. Let's see what we can do with this. So let R be the region bounded by f of x equals radical x and the x-axis on the interval from 1 to 3. So this is where the fundamental theorem is important, because we don't have formulas for like the square root of I plus 2 or anything like that. Like, we don't know a formula for that. So we wouldn't be able to do our thing where we're like, oh, now we'll use the formulas we memorized, because we didn't memorize formulas because we don't have any for these. So let's see if we can do it. Set up a right Riemann sum to approximate the area. All right. Well, we need delta x. So delta x is 3 minus 1 over n, so 2 over n. X sub I is going to be where we start plus I delta x. So 1 plus 2I over n. So our approximation will go from 1 to n of, so f of x sub I, so the square root of 1 plus 2I over n, and then delta x, so 2 over n. So that's where, like, that's a weird thing. Like, we don't know any formulas for that. So like, what would we do? There's kind of nothing to do. So what you do at that point is you just pick values of n, right? So if n equals 50. So what we're going to do is we're going to write out the first 3 and the last 2 terms of the Riemann sum. The reason I think this is important is that there's this entire classification of problems where all you're doing is looking at expanded Riemann sums and deciding like, what's the function, what are the bounds, and then you apply the fundamental theorem to it. So let's see if we can, so we're basically creating those problems. So we're saying that the integral from 1 to 3 of the square root of x dx is approximately, so we're using 50, so n is equal to 50 here. So when n is equal to 1, no, when I is equal to 1, so we're going to get I is equal to 1, we get the square root of 1 plus 2 over 50, sorry, and then times 2 over 50. That's 1. When I is 2, we get 1 plus 2 times 2, so 4 over 50 times 2 over 50. When I is equal to 3, we get the square root of 1 plus 6 over 50 times 2 over 50. Then we're going to do a plus dot dot dot. I'm also going to move this. You got to use your space well, and I do not. Plus dot dot dot. Okay, so the second to last one is 49. 1 plus 2 times 49 is 98 over 50 times 2 over 50. And then 50. 1 plus 100 over 50 times 2 over 50. There you go. Okay, so it's definitely approximately that. We're just, every time we're just doing base times height. So the base, ooh, there's a squirrel going nuts in a tree. I don't know if you can hear that. They sound like ducks. It's really weird. Just kind of quack. You're just gonna sit there and do that, I guess, for the rest of the video. So Oh, he stopped. Nope, he didn't stop. I don't know if you can hear him or not. Base height. It's also, that's a squirrel. I don't know if you can hear it. Height, and then base. I wish he would just shut up, but he won't. All right, it's base times height all the way through. It's making me anxious. So sometimes when you're writing these, it's like it's easier to see like oh my God. If I had like a water gun, I would shoot at him, but like I don't. And so he's just gonna keep going. So it's sometimes better to write this as like 2 times 2 over 50, 3 times 2 over 50, 49 times 2 over 50, 50 times 2 over 50, because then it's really clear what your x sub i's are. I think that that's a really good idea. Use a limit. Don't evaluate it to turn the Riemann sum into a definite integral. So this is just saying that the integral from 1 to 3 of the square root of x dx is actually equal to the limit as n approaches infinity of, what could it be doing? It's just sitting there quacking. The square root of 1 plus 2i over n times 2 over n. So that's what it's actually equal to. Okay, do I know how to find this limit? Not really. And this is like one of the key things. Like I don't really know how to find that limit, but what I do know how to find is I know how to find this because I know how to use the fundamental theorem. And since I know how to find this, it means I know how to find this. So it's like an indirect way of doing it. It's kind of like the limit definition of the derivative, right? You get a lot of limits. You look at them and you're like, I have no idea how to find that limit. But I recognize that that limit is actually the definition of the derivative, and I can find the derivative. Same deal here. So I'm going to say 1 to 3 square root of x dx. All right, I need an antiderivative of this. So this is x to the 1/2. So I'm going to add 1, get 3/2. So 2/3 x to the 3/2. And then from 1 to 3. So this is the weird notation that you use. It's a such that, and then you put the lower bound and the upper bound. So that's, I think the first time we've done that, that's the notation that you use. So this is our antiderivative. It's like, is it upset? I have to assume it's upset because it's just going on and on. Oh, he's crawling away. Good. God. Okay, so that's our antiderivative. And then we do such that 1 to 3. And it's like a bookend for our integral sign. And then what you do is you're going to plug in the upper bound, 2/3, 3 to the 3/2 minus plug in your lower bound, 1/3, 1 to the 3/2. And then you can factor if you want or whatever. Actually, it's not going to look any better, so I'm just going to leave my answer like that. Now, why don't you need plus c in this case? So this is important info here. So what color? Red, I guess. You don't need plus c this time, or any time when you're doing the fundamental theorem, because if we do like f of b plus c minus f of a plus c, no matter what c is, this is always just going to be f of b minus f of a. So we don't bother ourselves with plus c when we're using the fundamental theorem. It's like the only time that you don't care about plus c. We don't care because we're just going to fundamental theorem it, and the plus c here and the plus c here, when you subtract, they're just going to cancel out. So it doesn't make a difference. Like you could write this thing plus 50, right? And then when you plug in 3, you'll get this thing plus 50. When you plug in 1, you'll get like this thing plus 50. When you subtract them, 50 minus 50, gone. It doesn't matter what number you choose. So you don't use plus c on these, but that's like a textbook example of fundamental theorem right here, right? You have this problem, you find an antiderivative for this, which is this, and then you just evaluate it using fundamental theorem. It's amazing. It's so fast. And it gives us access to evaluating crazy, impossible looking limits. So this is another type of limit that looks impossible, but is actually like quite doable indirectly. A lot of derivative limits look impossible, but they're just derivatives. A lot of definition of a definite integral looks impossible, but it's actually just a definite integral. So the fundamental theorem swoops in and saves us. All right, I'm going to stop this video here. I'll be back in the next one, and I will see you there.